Hello, everyone, and welcome back to Techignite, a speaker series organized by NTU College of Engineering. My name is Luke, your MC for today. Today, we are honored to have Dr. Jatin Kumar, who will be sharing with us about the very interesting work underway in Xinterra. Xinterra specializes in combining data science and artificial intelligence with material science expertise to accelerate material research and deployment. If you are tuning in to listen, I'm sure that you are looking for opportunities in the future. So remember to listen intently, take note strategically, and scan the QR code to put in any questions that you have. Now, may I have the honor to welcome Dr. Jatin to begin sharing about Xinterra's work. Dr. Jatin, please.
Apologies. Yeah, hi. My name is Jatin. I'm the co-founder and technical lead of Xinterra, and Xinterra is a materials informatics company that is focused on, well, fundamentally changing the world by developing sustainable materials. Because of course we do have a very urgent and looming crisis on our hands in the form of a climate crisis. And so, why is it so important to fundamentally change the way materials are developed? It's because inherently materials development is slow. If you think about materials development timelines and current R&D processes, you basically have, a new material takes many years to develop. You think particularly about one example that I love giving is Teflon, and Teflon took about 25 years from conceptualization to productization. And so this is really unmatched or very disproportionate to the degree of time that we're going to need to solve a lot of our climate crisis. And so fundamentally, this is where Xinterra is the space that Xinterra comes in. We want to speed this up radically, and by speeding it up, we aim to make it cheaper to do this R&D, and of course less limited, where possibilities become far more vast. And so pinging this or underpinning this is really the Xinterra Design Factory, which is the platform that we have that aims to solve this. And it's a combination of three things. The first is artificial intelligence systems, which are state of the art, but most specifically tailored towards material science problems. And so if you think about AI or general AI, it tends to have lots and lots of data. But in material science, data is a luxury, or it's very expensive to generate new data points or new novel materials. But at the same time, you have a lot of information about the materials. If you think about something in the realm of polymers, you have many descriptors. You have things like molecular weight, tensile strength, Young's modulus. The list is quite long. And so how do you harness that vastness of information, but less amount of variation? And this is one of the skills that we're particularly adept at to harness. The next part of our XDF is high throughput experimentation tools. So these are modular and interoperable tools. Some of them are influenced by robotics. Others are influenced by this concept of proxy experiments, which is basically to diagnose the property of a material rather than completely characterize it. And all of this information, all of these tools allow us to rapidly collect information about our systems or our materials. And so this feeds into our AI, particularly because with the vastness of data, there's more to train with the AI, and this becomes exceptionally powerful when paired with the fact that our AI can handle small amounts of data. And then, of course, underlying all of this is a deep domain expertise in material science. In fact, through the founding team, we have a combined century of experience in all of these fields that you see on the left. And in many cases, a crisscross or a multidisciplinary expertise in material science. And so how does this change the material development journey? Now, if you look here, this is a very linear and a very incoherent approach, which is typical towards most materials R&D. You start with an opportunity, you define your materials, you design your experiments, you conduct low TRL R&D with validation, with several steps of validation, moving towards higher TRL or technology readiness level, before you go into final validation, scale up, and commercialization. Now, at any one point in time, your experiments could fail, your materials development could fail, and you have to go back to the start. And that's what these loops here signify. And so what happens is it's a cyclical process where you keep going and going and going until you can proceed to the next sort of step, kind of like a game of snakes and ladders. And where Xinterra chooses to break that mold is really the short circuit the entire internal process to go straight to high TRL R&D or even final validation. And how it does it is using this XDF platform. We're able to create these microcycles, learn fast, fail fast, and really use the AI to guide us towards that final target, whatever that final target is, based on your market need and opportunity. What we've seen is that this reduces your R&D cycle time by more than 10 times and significantly reduces R&D costs. So this is a very important step. It's not to say that we are completely disregarding the thing in the middle. It still happens. It's just that it happens in a more sort of well-controlled way, guided by data and guided by the machine learning. And so how does this equate into an actual experiment or an actual, an actual R&D cycle? Well, you start with the opportunity, same thing as the first bullet point that I had in the previous slide. And that essentially defines a problem statement. And we typically work with our customers. In some cases, we do our own internal development as well. And underpinning this, of course, is the generation of data, experimental data. And that experimental data could be generated by a company, by a customer. It could be generated by us in the form of a customizable high throughput experimentation tool. So generation of data, measurement of properties is what we start with. Now, of course, typically you'd have the data in a very simple format. Most of the time, most researchers tend to have their data in an Excel format. However, there are certain nuances in that data that are not always expressed. Certain things like limits of solubility or incompatibility of reagents. These are very common sort of underlying things that are not written in an Excel sheet that describes your data. However, this is very important. And so we take those things into consideration, clean up the data and prepare it into what we call the materials descriptor framework. And so this materials descriptor framework is what is then used and fed into a machine learning algorithm. Now, the machine learning algorithm provides two key sort of sections of information. The first is it gives you insight into your data. Simple things like the correlation of your data, certain positive correlations and negative correlations between parameters in your final output property. It could also give the importance of different input parameters, your different reagents or your different, processes on the final output property, and we call that feature importance. And all of these can be used and very useful in decision making, particularly when you're trying to refine your design of experiment or refine your material. And then, of course, what the AI can then do is design a new series of experiments that you could conduct in order to achieve your target. So targets could include, you want to hit a particular target product profile, or you want to hit a particular target performance. It could be cost saving and a hybrid of both, or it could be, process refinement, or it could be all of the above. And so this works in a loop where new experiments are suggested. It goes back into running the experiments, cleaning up the data, and then feeding it back into our AI platform. And so with working in these loops, what you're doing is a very similar cycle to what you saw with the traditional R&D, but it works much, much faster. The span of time that it takes is significantly shorter, because every experiment that you do is the most efficient or the best possible experiment that you could do to work towards your final objective. So how does this equate into a real life example? And so this is a company that we worked with, and it's a Singapore-based SME, and they're looking at industrial coating formulations. Particularly, they're looking at thermally insulative coatings. And so in reality, how it works is, or how they test it is, they take a metal substrate and they spray this coating on. And they subject that coating to a naked flame. Now, on the opposite side, they're measuring temperature. And the target that they're trying to hit is over 4 hours, the temperature on the opposite side cannot exceed 200 degrees Celsius. And so they've been trying for about 7 months. They tried about 69 different formulations. And what they found was that they weren't even close to achieving the target of 200 degrees Celsius. So on the right, you see 3 of the best performers and bare metals. Bare metals, the one in yellow, reference A. And you can see that shoots up really, really quickly. But even the ones that are coated, they also shoot up and go well beyond 200 degrees Celsius in less than 5 minutes. So the first thing we did was we took that data, and it was about 12 to 15 parameters, of different constituents, the fillers, the surfactants, the base polymers that make up your final formulation. And we compressed that 12 dimensions into 2 dimensions in order to visualize how effectively or how diverse the different experiments were. And what we found, which is no surprise to us, is that a lot of the experiments were very close to each other when compressed into a 2-dimensional space. Now, this is not why it's not a surprise to us, is because the first thing that we're taught in R&D is you change one variable at a time. And so there isn't a lot of diversity that you can get in a 12 with 12 parameters and 69 experiments. And so that's why it's sort of limited to one area. So that's the first thing that the AI was able to give us. The second bit of information was you had all these inputs, so all the different ingredients that go into your formulation, your paint formulation. It ranked the importance of each one of these ingredients on that final property, which is the temperature time profile. But one step further was it was also telling us whether it's negatively or positively correlated. So for example, input C, well, lots of input C would give you a very good performance, and less of input C would give you a poorer performance. But the opposite, so more of input O would give you a poorer performance, and less of input O would give you a better performance. So this was the first bit of insight into decision-making that was given to our customer. Now, another interesting thing was that with the ranking of the features, the customer was convinced that input A was the most important feature. But in this case, they're ranked descendingly. You could see that input C, F, and O were way more important than A. So this was news to the customer, and it actually helped them really refine their materials design process as well, understanding the more influential features rather and sort of weeding out the less influential features. Now, ultimately, when all this data was fed into our machine learning with the initial target of keeping it under 200 degrees Celsius for 5 minutes, what the machine learning did was it predicted that in order to achieve that, you actually needed to run these experiments in a completely different space to what had been sampled before. And so this all happened in less than 1 month, where the customer tried these formulations, and what you saw was that this met that initial target of 5 minutes, and far exceeded it. So it stayed under 200 degrees for 5 minutes. Of course, the following steps and the subsequent steps about this was to extrapolate then to 4 hours, which we did in 1 or 2 more cycles. And at the end of it, what the customer had was about 3 or 4 materials or 3 or 4 formulations that he can then now commercialize and sell. And this was done in a fraction of the time that would have taken him. If you think about 7 months and 69 formulations all in this space, you can probably extrapolate the time that it would have taken him to get there, and the opportunity cost that he would have lost. So this is the first major savings or a major step forward towards a customer realizing success through our platform. The second was a cost reduction in chemicals. So this particular company, they are making stabilizers, or stabilizers for PVC pipes. And so this is based on zinc stearate and a couple of different compounds. And so their ask to us was that their production cost was too high. And what they wanted to do was basically reduce that production cost, but keep the performance identical. And so what they gave us was this top time curve, basically a rheology curve, and told us to maintain the rheology curve. Of course, there were certain other features that we had to maintain, things like color, for example, linked to oxidation. And the target for us is keep the performance roughly the same within a certain amount of tolerance, and reduce our cost by 5%. That was their target. To them, anything exceeding 10% or anything up to 10% was fantastic, and anything beyond 10% cost reduction was unimaginable. And so again, with what we did was we took those 15 ingredients that they had, reformulated it with the AI, and suggested new experiments that they could run. And eventually what we found was we were able to reduce their cost while keeping the performance the same by 23%. So this was mind-boggling for them. And we took that same 15 ingredients, and in fact, we even reduced and eliminated some of those ingredients as the AI found them unnecessary for the performance. All of this done, again, in a matter of months. And this was not just done on one product line, but was done on 2 product lines with very similar levels of success. And so this is cost reduction combined with the previous example of performance targeting. And so you can see how powerful this platform can be just from the AI perspective. But I'll speak about one more example so that you understand a little bit more. And this is an example where we worked with a company that is looking at an electronic material. I can't say too much because we're bound by NDAs, but ultimately what they were trying to do was there's this performance metric that is over here, and they had hit a glass ceiling after 3 years of running experiments. They hit a glass ceiling of about 10, and they couldn't really go higher than that. And so there was a lot of data that they had, which they gave to us, and they had about 20 features. So the first thing that the AI was able to do was look at the 20 features, and these are compositional variables. They were processing variables as well. So it looked at the 20 features and realized that 9 were actually inconsequential in the final performance. So this was the first part. So it's a self-refining AI in a sense, where it only takes the data that's absolutely necessary. What it then predicted was that there was a possibility of doubling that performance, and this is what our AI predicted. Now, if you look very closely, you will see some elements of the first example that I showed, where you needed to sample in areas that were previously, or you needed to do the experiments with some of the features in areas that were previously unsampled. Examples are things like feature 3, where you needed a significantly higher value, or feature 6, 5, 9, where all of the sampling points were in gaps. And so when the customers did these experiments physically in their lab, what they showed was, yes, definitely that they did double their performance. And again, 3 years of work on this, and we achieved this in 6 months. We doubled the performance in 6 months. What you don't see in this deck of slides was that we also predicted that there was a possibility of tripling the original performance and going up to a metric of around 30. Of course, at that point, the project ended and we didn't proceed any further. But really, the AI could continuously keep optimizing up till the actual physical limit of the system that is bound by the thermodynamics of the system that you're in, rather than settling for what is good enough for now. So now I want to jump gears and talk a little bit. I've been talking a little bit about AI, and I want to talk a little bit about our high throughput experimentation platform, combined with a data-driven approach. And so the platform that you see here, some of you may be familiar with tools like this. This is an automated pipetting robot, and we were doing something really simple, which was a formulation of 3 different materials. There was graphene, surfactant, and hydroxypropyl methylcellulose, which is a film-forming polymer, sustainable polymer. And the target by the company that we're partnered with here was to understand the relationship between different surfactants and graphene towards achieving conductive films. And so what you see here was a formulation. Each each well plate which is being pipetted into is a unique formulation completely. A different ratio of graphene surfactant, a different type of surfactant, or different ratio of surfactant, and a different amount of film forming polymer. This pipette is touching the tips to reduce droplet and to increase accuracy. But other things that the pipette was able to do, and what we customized the system towards, was to do mixing of different solutions of different viscosities, and then finally drop casting onto round glass wafers. And that's what you see on the left. So all these little droplets, each one of them is a unique combination or a unique formulation. Now, when dropped and dried, what we did was test out these materials for their electrical conductivity using 4-point probe measurements, which were again automated using a setup that you don't see here. Now, all of this was realized in a matter of hours. What it would have taken a traditional research lab to do would be probably in the time span of months. And so we shrunk everything that was done in months into a mere set of days. And so the results that you see on the left clearly paint a picture of a data-driven approach where you see the relationship of each one of these different surfactants and the minimum amount of graphene that you would need to achieve a conductive film. And so this was more of a knowledge building exercise and a data building exercise. A step forward from here was the application of this technology towards one of our customers, where we've helped them to develop graphene-based paints and graphene-based coatings using a very, very similar approach targeted towards a whole range of different applications, ranging from electronics to inks to other potential applications as well. And so this sort of all what I've just described fits into a business model, one of our two business models, and that is the as a service model, where we engage in a service with a customer. We help them solve a very, very finite problem, and we use our AI models ultimately to help them realize their goals in a very, very quick way. We work in a high touch mode where we work very closely to understand the customer's problem and then translate it into deliverables through our system. But of course, there is a very powerful platform that we're sitting on, and we're using that to generate our own materials IP as well. And the domain that we've chosen to go into is materials for CO2 capture. Now, what we intend to do with this platform is, of course, with the IP that we build, to work with customers to do to license that IP, to look into joint ventures, and I'll speak a little bit more about this now. So, what is our carbon capture initiative? Well, ultimately, it's about using our concepts of high throughput experimentation together with AI to realize new materials. And why is new materials such an important thing? Well, traditionally in carbon capture, you have it's binned into two categories. One is direct or point source capture, typically, things that are coming out of exhaust and flue gas. And then there's direct air capture. Flue gas, typically high temperature, high pressure, and high concentration of carbon dioxide. And direct air capture is basically capture from the atmosphere, low carbon dioxide concentration, ambient pressure, ambient temperature. And so what we're focusing on, and so what the world and a lot of companies focus on is building the engineered systems that allow them to capture this carbon dioxide. But very few actually focus on the material itself, the stuff that is doing the work of physically capturing the carbon dioxide. And so this is the space that we identified an opportunity. And so in order to make these materials and test them, we're leveraging on a system that you saw on the previous slide, along with a testing rig, a prototype of which you see on the left. So what this system allows us to do is it's a high throughput environmental chamber. It allows us to precisely control the environment. So I gave the examples of direct or point source capture, and I gave you the example of direct air capture, both vastly different environmental conditions. And then ultimately it's paired with AI to conduct in our experiments in an intelligent way to extract all the data that we need in order to characterize that material for its ability to capture carbon dioxide. And so what we started with this system that you see on the left was the ability to measure one sample in a day, one condition in a day. And this is in line with what is done in academia and industry, where you typically can measure 1 to 2 samples a day using techniques like PET and TGA. Where we are working towards and what we are at right now is the ability to measure 50 samples in a day. And so this is where the high throughput really kicks in. And so you can make samples in the matter of hours, and you can test samples in the matter of hours. And that's really what's required in order to feed enough information into our artificial intelligence to come up with those new materials. And so, if you think about it, typically what you see are different categories of materials that are binned into classes like this. And you have different ways of assessing them. And that's the initial database that we've built, these what you call homo materials, if you want to call them that. And where AI is guiding us towards is, novel combinations of materials that are non-intuitive, to combine these materials together and work towards a forced serendipity in achieving some of the targets that we've envisioned. And so some of our visions would be to democratize carbon capture and make everybody part of that carbon capture story. And how we intend to do that would be to embed carbon capture materials into things like paints and coatings. So the walls of your home could be captured in carbon dioxide. Every single HDB in Singapore could be covered in carbon capture material. And even in textiles, so every garment that you wear is passively capturing carbon dioxide every single day. And so that's sort of the disruptive technology that we're thinking of in order to put that dent in the rising CO2 levels. And so very briefly, thinking about the kind of data that we're generating. So what we have is that carbon capture rig that I mentioned earlier, that is generating a large multimodal data set. So lots and lots of data that we're collecting through 3 fundamentals. The first is, of course, proxy measurements. So we get qualitative and quantitative diagnosis of how material is performing. Precise environmental controls that I mentioned earlier. So the ability to replicate not just vastly different, high concentration, high temperature systems versus low concentration, low temperature, but even, various parts of the world. So, replicating an environment in an arid part of the world versus a tropical climate. These are things that we can do. And of course, judicious baselining. So ensuring good data precision. Why is data precision so important? Data precision is extremely important because there isn't a set testing method and evaluation method for carbon capture materials at this stage. And in fact, there is a high variability between methods. So basically very low precision. In fact, the recent statistics show that it's about measurements of materials are about 7% reproducible based on literature data. So this is something that we're taking a lot of care and concern into. So ultimately, what we're building and the data that we're building is real world data. It's not theory, it's not simulation, because it's based on that simulated environment that we show. And things that we control at the moment are particularly gas concentration, pressure, airflow, and humidity. So the data behind the data set, and you can see, really each one of these is painting a story about carbon capture based on different starting carbon dioxide concentrations from high to low. It's giving us high fidelity kinetic plots, so we know how quickly a material absorbs carbon dioxide, how secure that carbon dioxide capture is, and whether that carbon dioxide re-releases. This is an example of it re-releasing, and how much ultimately carbon dioxide a material can absorb. So there is a multimodal response that we see, and we're starting to see sort of dependencies beyond carbon dioxide concentration. Things like temperature, pressure, humidity are critical things. And of course, with these correlations that we see, it helps us to drive DOE, materials design, and decision making, very similar to the examples that I gave earlier, the ones that we did with our customers, and ultimately helps us to link scientific hypothesis to unique materials performance. And so, sort of understanding why this sort of behavior happens There is a scientific hypothesis behind it, but we have the data now to show how that links together. And then, of course, the final piece is bringing in the artificial intelligence. And so you could see some of our absorption curves that we typically see, the carbon dioxide absorption curves. And what we've built are a series of empirical models that eventually go into artificial intelligence that are able to capture the experimental performance and express them mathematically. This includes, certain special characteristics like the one that you see here with the absorption, initial absorption, and the release of carbon dioxide. Similarly here. And ultimately, what we're using this to do is help us to inversely find new materials that could fit the profiles that we require for a particular application. Potentially something in textiles where you need it to absorb at ambient temperature of 35, 36 degrees and then release maybe when it goes into the washing machine at 40, 50, 60 degrees, whatever the temperature of the washing machine is. And so these are some of the sort of ideas that we're trying to embed into the machine learning. And then ultimately combining that raw data with these empirical models allows us to come up with powerful predictions and the ability to pick the right experiments to run so that we can continue to work towards our target product profile. So this is a snapshot of our database, and really you can see the progression of materials where we started somewhere with lower absorption and low absorption rates and low amount of carbon dioxide, and we're working towards a significant jump. This is the first ever comprehensive database of commercially available carbon capture materials, and this is based on commercially available materials. And we're working now towards these new formulations, which will start populating this list. But ultimately what we have is real data. It's real world data, it's reproducible data, it's not theoretical. And it's something that equates very quickly into what can happen when it's deployed. And so with that, this sort of summarizes the work that we're doing. And of course, I'd like to introduce the team. So we have the seven founding. Well, it's a founding team of 7 and an operational team of 4. One face you might find familiar, Professor Kedar, who is faculty at MSc, who is a co-founder and a scientific advisor to Xinterra. But we have an operating team of 4 and a larger team of 6, soon to be 7, along with several alumni from NTU. And so ultimately, how are the 7 of us and a couple more planning to create impact? And that is basically, to summarize the whole statement, to radically accelerate the creation of new materials, especially materials that enable sustainability using our platform of artificial intelligence, high throughput experimentation, and deep domain expertise in material science. And with that, I'd like to end by saying that this is what we do, and I'm happy to take questions now.
Thank you, Dr. Jatin, for your sharing. I'm sure our audience have many burning questions after listening, and we would like to bring your attention to the QR code at the bottom of the screen. You may scan the code and it will direct you to slido.com, where you may input the hashtag Techignite to post your questions. So for our next segment, I'd also like to invite Nanyang Associate Professor Kedar from NTU School of Material Science and Engineering, who will be joining Dr. Jatin for the Q&A session. So a very warm welcome to the Q&A panelists, and let's begin to address some of the questions that the audience has sent in. And I would like to address the first questions that is addressed to, I think Dr. Jatin. All right, so the first question is, thank you, Dr. Jatin, for the sharing. And I understand that you are incorporating AI to project and gain insights from data so that less iteration is needed. However, I'm curious, how using actual materials instead of simulation helps to save cost. Can you elaborate more on this?
Yeah, this is a great question, and we have been asked this question before. So if you think about simulations, things like DFT, MDS, typically what is done is that you're calculating from first principles, and ultimately this is an approximation to the real world performance. However, it sometimes isn't, doesn't directly translate into a real world performance. And so ultimately, you're going to build your material in reality, you're going to test your material in reality, and you're going to use and deploy your material in reality. And so the best way in order to work towards your target is to train your AI with experimental data. Sure, simulation data can always augment and make your algorithm a little bit more robust and maybe require less experimental data. But ultimately, experimental data is king. It's the one that will tell you exactly what's going on with your material in a real world application.
Thank you, Dr. Jatin, for the question. So for the answer. So to sum up his answer, it is about using real data, because now we also have simulation data, but you also need real data to incorporate based on that, so that the material deployed is according to what is needed. And the second question that I get from the audience is directed towards Professor Kedar. So the presentation, right, is about using AI to replace the notion of pure trial and error. And then, as everyone knows, NTU is ranked first globally in the material science domain, even above global universities. So may I ask how NTU is incorporating technologies to achieve this?
Yeah, so that's a great question. In fact, thanks first of all to Jatin for introducing how AI can actually help in the materials innovation process. And it's a good question to understand, how do we as a leading material science department incorporate AI in different forms of learning and in different forms of training for the students, as well as perhaps going out into the workforce, right? So first thing I'll say is the School of Engineering itself, and perhaps even at the university level, introduces an introduction to data science and artificial intelligence course, which is for all undergraduates. It's a university-wide course that's offered to everybody, and every department has its own flavor of that course, right? So if you're a first year or second year undergraduate, then you will be exposed to this course. And in materials, we find that what we would like to do is emphasize the statistics behind the data science a little bit more, because underpinning all of the cool AI is actually the statistical interpretations, right? That's what drives all the algorithms. So we teach the concepts, right, of how would you actually, for example, do visualization, pattern recognition, how would you build regression models, classification models, perhaps clustering, anomaly detection, etc. So that's the foundational step, right? Going beyond, MSc is actually pretty amazing, because as a part of the curriculum, students get to do internships, like full semester internships with real industry, right? And that's a fantastic experience, because once you're sort of armed with that data science arsenal, when you take the basic science course, you are actually reasonably good at using Python, for instance, as a programming language to do data science out in industry. So you can actually be valuable when you do your internships with industry. One can imagine, for instance, and having an industry internship with Xinterra, perhaps, where the students can actually go and spend a semester helping Xinterra do its high throughput experimental development or building new AI algorithms for materials. But we haven't stopped there. In MSc, what we actually have is recently announced is a specialization, a material specialization for undergraduate students. That actually involves 2 courses, Intro to Python, the data science course. In addition, you have to take an online module. There are many available everywhere around the globe, and that's actually really nice, an online module on AI. And you have to do your final year project on an AI-related subject. And there's various faculty members within NTU MSc who are actually doing AI-related projects, me, myself included. In fact, a good example of this is the 2 final year project students who actually are currently working at Xinterra working on AI and materials development. So when you actually finish all of these requirements, and there's a final 4th-year course that I'm teaching in MSc as well, towards the specialization, which is more advanced, which deals with optimization, autoencoders, deep learning, etc. So that's actually a more advanced level course. This is beyond data science and intelligence. So this is how we see that, data science is basically a very critical tool to augment your learning and to augment material science and all the fundamental knowledge that you learn from materials engineering anyway. And those are the steps we're taking in that direction.
Thank you, Professor Kedar, for sharing. And that was a very insightful response about how our school is trying to adapt to technologies and incorporate this. And a very relevant follow-up on this question addressed to Dr. Jatin is, if Xinterra is employing, what kind of qualifications is it looking for? What kind of technical and non-technical skill sets that is looking for in graduates? And any specific level of requirement? For example, at least professor, master, or any research projects that students have to show? Yeah.
Thanks for that question. So it's actually, we're a small, young startup, but I think that with any startup really, is the need to have a disruptive mentality, the ability to work fast and focus and change with shifting priorities. Because sometimes, you could shift priorities several times in a month, let alone in a research project. And so this is one of the key things that we look for. That's mindset, the ability to make things happen in almost a hacker mindset. So mindset is one. Now, of course, it's based on our needs at the moment. In some cases, or in most cases, a graduate degree is enough. But in some cases, you need some specialized knowledge. It comes from the synthesis side of things, the knowledge of performing these synthesis experiments, wet chemistry knowledge. In some cases, it could be coming from the machine learning side of things. And we just hired actually one of an NTU alumni who is an MSc alumni actually, but had a keen knowledge and a keen motivation towards data-driven approaches, and he's joined as part of our data team. So really, it's understanding the need of the moment, and those needs change quite radically. But really, it's that hacker mindset, the ability to think laterally rather than with the mold, which is extremely important for radically and disruptive technologies that similar to any AI-driven approach or the kinds that Xinterra is looking at.
Thank you, Dr. Jatin. And mentioning about the disruptive mindset, I think NTU is a good place for students because we have a lot of hackathons and we train students to think differently because that's what technology is about. And to our next question about this is probably addressed to Professor Kedar. And so relating to the materials research, what are some of the other constraints, like besides time, what are some of the other constraints or challenges that the industry and all the academia often face?
So I mean, there are constraints in terms of, first of all, resources, right? So how do you maximize the utilization of resource, right? So if students are familiar with this sort of concept in materials research, typically, I think Dr. Jatin showed a slide right in the beginning of his presentation as to why does it take 25 years to develop a material and take it from lab into the market, right? So part of the reason is that the resources required for you to scale up a technology that you discover in the lab are very different and can be orders of magnitude more expensive than just demonstrating something in a research lab, right? So the scale-up problem is typically called, like, let's say, the valley of death. But there are two other additional considerations, right? So for instance, sometimes impact comes from the fact that you have to think about the manufacturing process right from the beginning. So when you design for a particular application or a particular product or a target product profile, as Jatin mentioned before, you have to think about the full innovation chain from how you manufacture something, not just what you manufacture, but how you manufacture something. So that is an additional constraint that actually makes the innovation challenge harder, right? And with AI, a good solution is that you can think of the system approach directly, right? You can not just think at the material level, you can think at the device level, you can think at the system level. When you combine all of these, it basically becomes a data frame for those who understand material science. So your data frame should have inputs from all of these different levels. In AI speak, we call it, let's say, multi-fidelity or sort of approaches. And once you have that full approach considered, you can then use the AI techniques to solve for it and optimize for it, considering all the way from, like, let's say, an atom all the way to a final device, or even a ton of some chemical that you've manufactured, right? So those are some constraints. And the main constraint that everyone can help with is talent, right? We want the talented students to not just run away and work in banking. And we want you guys who are talented to come and work in materials informatics, work for materials, because what you see and you feel around the world is really what drives the world around you, right? You cannot have AI just driving battery operated vehicles. You need to have sustainable batteries themselves that are manufactured through this process, right? So we need you to continue to innovate and work in this space. So I think those are our main constraints.
Thank you, Dr. Kedar, Professor Kedar. And to further complement on this answer, Dr. Jatin, do you have anything to add on? Like the past case in your industry that you have faced, what's the development time frame, or what's the typical constraints that your own company often face as a SME?
Well, I think there are many constraints that we face. A lot of it is of course the fact that when you're a startup, everything is about running. You're constantly chasing timelines, and you're trying to get out, get technologies out as quickly as possible. Of course, with what I showed earlier, our technology makes it a lot easier for us to roll new materials out. That doesn't take away the fact that we do have our challenges. Of course, if you compare research in an institute such as NTU, basic resources like equipment are a lot more difficult to come by. And so, simple things like, for example, an FDIR is something that a young startup with a low CapEx budget wouldn't be able to afford, but it's sort of almost trivial in a research institute. So these considering how we're going to circumvent some of these challenges is part of our regular and frequent discussions. And it almost has become a state of mind where you're constantly thinking about this. Of course, the other challenge is manpower, and manpower seems to be a pervasive challenge even in university research groups. So that is the second thing. And of course, as Kedar rightfully mentioned, having engineering students go off into banking really hurts us, hurts the development of scientific development, especially in Singapore. And so this is an important key factor. And of course, the last thing that I wanted to say was in a small company, it's both an advantage and a disadvantage, where you have to, and every single person has to bottom line everything. So cleaning, ordering chemicals, doing administrative work, but at the same time coming up with technical development and interfacing with customers. All of this is typically done by the same people. And so this is resource constraint, but at the same time, the buck stops at you, which means that you have full control over how well or how poorly something goes. And so that's some of the challenges that you face in a smaller company. But of course, the dynamism and the fact that you have that said control makes it a lot more interesting, a lot more engaging, as opposed to just sort of being siloed into one job function.
Thank you, Dr. Jatin. And I understand that with an SME, there are often many constraints, but I believe that with the talents that is available in Singapore, I think you can source the talents that is needed and further develop your operations. And also there are some more questions from the floor. Question number one is, For carbon capture, I'm curious as to whether it is feasible for such materials to be used for purposes such as paint or textile, because captured carbon will eventually become saturated and affect the functionality or appearance of the product, such as textile, making it dirty or unsightly after use. So to sum up, the question is about whether this carbon capturing function affects the material's functionality. And I think I can open this question to either Dr. Jatin or Professor Kedar. Maybe
I'll comment really quickly. So first things first, I think capturing carbon dioxide, it doesn't actually physically alter, or from what we've seen from our experiments, it doesn't actually physically alter the appearance of these materials. And so that is a separate point. I do not think that it would actually physically, deteriorate the appearance of its final deployed materials. So let's talk a little bit about carbon capture and the reversibility of carbon capture. So there are technologies out there where carbon is permanently sequestered and bound for a very long time, and the energy required to release that carbon dioxide is extremely high. And then there are also technologies where the carbon dioxide that is captured can be released with a reasonable amount of energy. And so if you think about something like a textile, what we're envisioning is not just a one-way absorption where it's locked in that t-shirt, for example, forever, but really an ecosystem where over the course of the day you'd capture carbon dioxide into that t-shirt, and then at the end of the day when you throw it into the wash, that carbon dioxide is recovered and then can be used for any other application as a feedstock. And that is really that cycle that would see a long-term benefit. In fact, this is actually some of the technology that is used by the energy industry. So you have power plants with their thick chimneys or thick high concentration carbon dioxide, and what they have are scrubbers that remove that carbon dioxide, collect it, and you get high purity carbon dioxide that can then be used for several other applications. And so in the energy industry, what they use it for is they actually pump that carbon dioxide back underground in order to liberate remnants of fossil fuel that are trapped in these underground reservoirs. So that's one potential application. Other potential applications are to just use carbon dioxide for feedstocks into various range of applications. It could be simple things like in the beverage industry for drink carbonation, or in the food industry generally. It could be, and there is increasing work into using that carbon dioxide into converting it back through a catalytic process into fuels. But yeah, that's essentially the cycle that we're looking at, the regenerability of carbon dioxide. So some of the examples that I'd actually shown, some of those materials are regenerable with small increase, or what you call a temperature swing, so an increase in temperature and a pressure swing, or a decrease in pressure to liberate the carbon dioxide.
So if I understand your answer correctly, so the material will capture the CO2 in the air, and then when you wash it, the CO2 will be offloaded into the water, and then the material can continue to perform its functionality, and then the point of saturation will not be reached or will be reversed, right? Is that what you're trying to say?
Yeah, it's you can saturate it and then release it. It's kind of like battery, charging and discharging a battery.
Yeah, thank you, Dr. Jatin. And there's one more question from the floor. My question is about the safety of the use of AI. If the AI is constantly fed data to maximize efficiency of the material product, will there be scenarios where combinations of materials that are toxic to humans end up in the formulation, but are neglected because they are much more efficient? Yeah, so I will open up this question to.
I can take that. So it's a great question. I mean, it's very important to think about this question as well when you optimize for something. But the key here is optimization, right? Many a times the restriction as to what materials you can use in the initial state of design will depend on the toxicity of them. So we can account for that as either a constraint in the optimization algorithm in the AI, or it's something where we can say it changes our decision boundary, right? You choose not to use certain materials. Of course, the more interesting question perhaps is what happens if something toxic emerges unexpectedly from a certain formulation, right? So you could envision something coming together which you do not expect to have toxic properties before, but does after it becomes a formulation. So that is a difficult question to answer a priori. But of course, what you can do is have testing, and typically many formulation companies do this anyway. They have toxicity metrics, biocompatibility metrics, and you can include those tests before it becomes productized. So what you would then do is apply a filter at the end of the AI innovation process to ensure that the toxicity metrics and standards are still met, right? So I think both are acceptable and something to think about right from the beginning, right? And I think you can address in a rigorous fashion both of those questions through an AI approach.
Thank you, Professor Kedar. And this question is indeed tricky because that's one of the most prominent challenge in implementing AI. AI is often that you are not very sure, 100% sure about what's going to come out of the model. And that's why there's a lot of process and when the person implements it, the person needs to think really hard about what possibly could go wrong. And anybody here with training in data science and AI will totally understand this this headache. And yeah, I think we have come to the end of today's session. And due to time constraints, yeah, we have to conclude the session here. On behalf of NTU students, I would like to extend heartfelt gratitude to Dr. Jatin and Professor Kedar for setting time aside to share with us about your exciting and invaluable work. I would also like to thank all of you for tuning in. And last but not least, there's one last Techignite talk tomorrow on the civil aviation sustainability, a hot tech topic nowadays. As an international air hub, Singapore is trying to lead the transformation of the industry. And you can scan the QR code to register for tomorrow's session. Be sure to tune in to listen. See you soon.